organizers, Professor Yeonjun Kim and Professor Daniel Hilhorst, for inviting me and giving me this opportunity. I'm very glad to talk here. Today I talk about this topic, pattern formation in chemotaxis-growth system. Mainly I talk about numerics, about on the pattern formation arising in the chemotaxis-growth system. This is joint work with Professor Kosuke Kuto from the University of Electrical Communications and Professor Toru Tsujikawa from University of Miyazaki. First, I talk about chemotaxis a little bit. So as you know, probably as you know, chemotaxis is an oriented movement of biological species, which is caused by a gradient of the chemical substance around them. So please look at this picture. So this region is concentration is low, chemical concentration is low. On the other hand, this region, chemical concentration is high. In this case, cell, this is cell sense the gradient of chemical substances. Then this cell moves to the higher concentration area of chemical substances. This is called chemotaxis. But strictly speaking, this is a positive chemotaxis. Chemotaxis is used around us. For example, in our body, this is a famous example of the chemotaxis effect. In our body, some extermination of bacteria and viruses due to white blood cells. In order to exterminate the bacteria and virus, white blood cell sense the gradient of some chemicals, then goes to the higher concentration of the area. The other example is the expansion process of cancerous cells. And the most popular chemotaxis effect is the following: the bacterial colony patterns. In particular, some bacteria, for example, E. coli and Salmonella difficile, such types of bacteria make some beautiful pattern, beautiful regular pattern, colony patterns. Then they use the chemotaxis to make such beautiful regular pattern. So in order to understand such bacterial colony patterns, a chemotaxis system is a growth term proposed. This is the most basic chemotaxis growth system. In 1995, Woodward et al. Proposed this system. Here, U is a density of cells, and V is a concentration of chemical substances. Please look at this term. This means U sense the gradient of V. Then U move to the higher concentration area of V. So this means chemotaxis term. And chi of V here is a sensitivity function. And a lot of type of sensitivity function are proposed. Here, in this talk, we always use this linear sensitivity. Chi of V is equal to alpha V. Here, alpha is a positive constant. And F of U here is a growth term because cells divided. I'll talk about this growth term later. And in the equation for V, G of UV means a production of degradation of chemical substances. Here, in this talk, I always use these types of function form. Here is A U minus V V. This means U biological species produce chemical substance at a constant rate A. On the other hand, this chemical substance is evaporated by constant rate V. And D, here is a D. D is here. D means the mobility of the biological species. So if D, capital D, is large, then biological species moves faster. On the other hand, capital D is small. In such case, biological species moves slower. And finally, D, small d, means a diffusion coefficient for the chemical substance because chemicals diffuse. So I talk about the growth term on the F of U. So in the growth term, several growth terms are proposed. Here we mention the two growth terms. One is the logistic growth. Probably you know. F of U is RU 1 minus U. R is some constant. R means a growth rate. In this dynamics, F of U is like this, and 0 and 1 is a equilibrium. And U is equal to 0 is unstable, and U is equal to 1 is stable. So vector field is like this. So on the other hand, another growth term is cubic growth. Cubic growth is like this. Profile of cubic growth is like this. The function form is like this. Ru times minus 1 minus U times U minus A. So in this case, there are three equilibria. U is equal to 0, U is equal to A, U is equal to 1. So in this case, U is equal to 1 and U is equal to 0 and U is equal to 1 is stable. On the other hand, U is equal to A is unstable. So vector field is like this. Or if U is here, then U goes to 0. On the other hand, if U is here, then U approaches 1. So dynamics is rather different. So in the case of logistic growth case, chemotaxis with logistic term, this is well known. For example, as you know, due to chemotaxis effect, some pattern appear. This is a one-dimensional numerical simulation. Then some regular pattern structure is observed like this. So if we consider the 2D simulation, corresponding pattern appear like spot. As time evolved, these spots become regular and stabilize. On the other hand, this system exhibits spatio-temporal chaos. This chaos is found by Painter and Hiren in 2011. So what kind of behavior is observed? It's a quite interesting phenomenon is observed. This types of spatio-temporal pattern is appear. In this case, red means U, and V, blue means V. And I always use Neumann boundary condition. In this talk, I always use Neumann boundary condition. So we observe such types of spatio-temporal chaos. So then, when we consider the two-dimensional problem, then corresponding spatio-temporal behavior is observed. This means a black region means a high density of U, and white means a low density of U. So as time evolved, this spot doesn't stabilize. So this is a spatio-temporal chaos corresponding to this one-dimensional numerics.
So what's the difference between these two? What's the difference in the model of these two?
These two? Yeah, same, this one. but parameter is different. Yes.
Which parameter?
Yes, parameter is different. This one, this one.
I mean, which?
What parameter?
What? Sorry, I forget. But alpha is a 5 or 10, and alpha is a relatively small. Alpha is a 2. R is always 1.
Oh,
Yes.
6.
Yes. Then alpha and D, I change the alpha and D, small d. Then we observe two types of behavior.
So even initial data same, but
Yes, yes.
Alpha and D.
So alpha is important to obtain these types of behavior. Relatively large alpha, we observe these types of spatial temporal chaos. On the other hand, if alpha is a relatively small case, we have such types of spot pattern.
How do you know that the different value of alpha gives different kind of phenomenon? How you choose the value of alpha for this?
How do I choose alpha?
Do you have any threshold conditions?
I don't know. Yes, but we know the existence of such types of pattern, but we don't know the relation between alpha and D. Yes. So this talk I use the foreign growth term, cubic growth, because logistic growth case many research done by many researchers. So today I talk about the cubic growth like this. Then 0 and 1 is stable, and A is unstable. So in this talk, I talk about this chemotaxis-growth system. So this chemotaxis-growth system with cubic nonlinearity is proposed by Professor Mimura and Professor Tsujikawa in 1990. Today, main questions are following. Is there any difference in pattern dynamics between the logistic growth and the cubic growth? So if so, what kind of differences appear according to growth terms? This is the main question in this talk. So in order to answer this question, we first consider the constant solution. As you know, this system has 3 constant solutions. One is a UV is equal to 1, 1, UV is equal to AA, and UV is equal to 0, 0. Of course, we neglect this term, chemotaxis term, then U is equal to 1 is stable. But if we add this term, the constant solution, UV is equal to 1, 1, can be destabilized due to the chemotaxis-induced instability. So this means some pattern appear because of the instability. So if in order to know what kind of pattern appear, we investigate the global structures of stationary solutions. So from now we consider the global structure of stationary solutions of this system. In order to do that, we fix the parameter value R is equal to 1. A is 0.25. Here is A. R is here. And capital D is equal to 1. And alpha is equal to 2, relatively small case and relatively large case, 2 or 5. And small d, this parameter, we set this parameter d as a bifurcation parameter. So we change the parameter d, so what kind of global structure of stationary solutions. So by using computer, we obtain the numeric global structure of stationary solutions. So this is d is equal to 1, alpha equal to 2, r is equal to 1, a is equal to 0.25. Horizontal axis means d, bifurcation parameter d. Vertical axis means a solution of u of x at x equal to 0. So that means solution u at the boundary value of solution u. So this is alpha is equal to 5. So as you know, completely different types of global structure of stationary solution is obtained. So I explain briefly. So for large d, relatively large, for first I consider I talk about alpha is equal to 2. So if d is a relatively large case, then 1,1 solution. This is a constant solution. uv is equal to 1,1. This constant solution is stable, but at this point, bifurcation occur, pitchfork bifurcation occur. Then this constant solution becomes unstable because the solid curve means a stable branch, and dashed curve is a unstable branch. So at this point, this is a bifurcation point. So as a pitchfork bifurcation, as a result of pitchfork bifurcation, then some non-constant solution appear like this. This non-constant solution is stable, and d gradually small. Then at this point, this means a black square is a Hopf bifurcation point. So due to Hopf bifurcation point, this solution branch become unstable and connect to the singular solution because d is some diffusion coefficient of v. So in this case, connect to the singular solution. So this is some profile of the solution. For example, d is equal to 0.05. There is two stable stationary solution. One is this one. The other is this one. This one corresponds to this profile. This point corresponds to this profile. And this solution is reflected solution. This solution. So we can identify these two solution branches. And this solution profile is like this. Almost everywhere is A, but with some boundary layer up here. This is some solution profile with this point. So this solution structure connected to bifurcation point and a singular solution like this. On the other hand, alpha is equal to 5. Then in this case, for large d, this 1,1 solution is stable. But at this point, some bifurcation occur. Then this solution, this bifurcating solution is stable. And at this point, some pitchfork, Hopf bifurcation occur. Then this solution branch become unstable. But at this point, saddle node bifurcation occur. Then the solution branch turn and connect to this bifurcation point. This is the bifurcation point is on the uv is equal to AA. So this alpha equal to 5. In this case, this solution branch connected to bifurcation point on uv is equal to 1,1 and bifurcation point on uv is equal to AA. So solution profile is like this. This point corresponds to this profile, and this point corresponds to this profile. So, simple question is arises here. Which alpha value are the global structure stitched out? So, which, of course, we want to know these types of question. If we change alpha, which alpha the structure of global structure of stationary solution switch. Actually, in this case, I always fix d is equal to 1. D is this parameter. If d, capital D, is changed from 1 to 10, 1 to 100, then we obtain the quite similar bifurcation structure. This is alpha is equal to 2, d is equal to 1, d is equal to 10, alpha equals to 2, d equal to 10, alpha equal to 5. In this case, d is a relatively large case. D is equal to 100, alpha equal to 2. This is alpha equal to 5. So quite similar bifurcation structure is obtained. So this result means that the value of D does not influence to the global structure of stationary solutions. So in order to answer this question, we use the limiting system, d tend to infinity. So we use d tend to infinity. As d tend to infinity, we have a shadow system. D is here. So if d is infinity, then this term becomes 0. By considering the normal boundary condition, then we have this equation. So from this equation, we have a relation between u and v. Here, capital E is some constant, positive constant. On the other hand, in the equation for u, we use the integration by part. We have this integral condition. Combining these two equations, we have the shadow system. Shadow system like this. 0 is equal to equation for v and some integral constant, integral condition and normal boundary condition. By using this system is rather simple. So we can treat this system analytically. So by using this system, we can obtain the following result. The following theorem. The following result states the bifurcation structure of stationary solutions depending on A and alpha. So theorem consists of 3 parts. One is if 1 over alpha is less than A, this case. So in this case, alpha is a relatively large case. So in this case, if alpha is a relatively large case, there exists a solution branch connecting a bifurcation point on V is equal to 1 and the bifurcation point on V is equal to A. I explain later for more detail. Second one is this one. If 1 over alpha is between A and 1, there exists a solution branch connecting a bifurcation point on V is equal to 1 and a single solution. Third case is the following. 1 over alpha is greater than 1. In this case, alpha is less than 1. So relatively small case. So in this case, the following bifurcation structure is obtained. There exists a solution branch connecting a singular solution and another singular solution. So this theoretical result states that bifurcation structures are classified into 3 cases depend on A and alpha. But in this theorem doesn't say the stability of the stationary solution branch and exact global structure of the stationary solution. We know the existence of branch, but we do not know the stability and exact global structure of the stationary solution. So in order to get the stability and exact global structure, such information, we use computer. So by combining the theoretical result and the numerical result, we can say the following. 1 over alpha is less than A. This means alpha is a relatively large case. So if alpha is a relatively large case, there exists a solution branch connecting a bifurcation point on V is equal to 1 and a bifurcation point on V is equal to A. This means that V is equal to 1, constant solution. And this is V is equal to A. This is a constant solution branch. This means there exists a solution branch connecting to this bifurcation point and this bifurcation point. And numerically, we obtain the stability of the solution branch. This is stable. But at this point, some hop bifurcation occur, then this solution becomes unstable. And at this point, saddle node bifurcation occur, then branch turn and connect to this bifurcation point on V is equal to A. For example, in this case, D is equal to 0.25. Profile is like this. Second case is the following. 1 over alpha is in A and 1. If alpha is moderate case, so we have the following result. There exists a solution branch connecting to a bifurcation point on V is equal to 1 and a singular solution. This is a numerical result. The stability is the following. The bifurcating solution is stable. But at this point, hop bifurcation occurs, then this solution becomes unstable and connect to the singular solution. Profile of singular solution is like this. Almost everywhere is A at a boundary, some boundary layer appears. And in this case, D is equal to 0.05. The profile is like this. So the third case is the following. 1 over alpha is greater than 1. So this means alpha is less than 1. So alpha is a relatively small case. There exists a solution branch connecting a singular solution and another singular solution. This is a quite new phenomenon because these two singular solutions, profile of these two singular solutions is like this. This solution profile is like this, almost A and boundary layer appear like this. On the other hand, this solution profile is like this, almost almost 1 and some boundary layer appear. This solution branch connects to two singular solutions. And in this case, D is equal to 0.0004. The solution profile is like this. Then in this case, this solution is unstable, but at this point, saddle node bifurcation occurs, then stability is recovered. Then at this point, hop bifurcation occurs, then this solution branch becomes unstable. We have the following three types of global structure of stationary solution depending on A and alpha. So case 3, in the case 3, for suitable D value, we obtain the same structure. In this case, D is equal to 100. Then in the chemotaxis-growth system, we obtain these types of case 3 type of bifurcation structure. This is a horizontal axis means D. Then this D is equal to 100. The solution branch connected to two singular solutions. And this is unstable. At this point, some saddle node bifurcation occurs. Then stability is recovered. Then at this point, hop bifurcation occurs. They connected to the other singular solutions. D is equal to 100, D is equal to 10. Also, we observe the case 3 type of global structure in the chemotaxis-growth system. So, we observe 3 types of global structure in the chemotaxis-growth system when D is suitable D is not so large, D is equal to 10 or D is equal to 100, we observe 3 types of global structure in the chemotaxis-growth system. So we can explain that this classification comes from this classification in the shadow system. So we can say the following explanation. This classification comes from the classification in the shadow system. So up to now, we have considered the global structure of stationary solutions. From now, we answer this question. Is there any differences in pattern dynamics between the logistic growth and the cubic growth? If so, what kind of differences appear according to growth term? Please look at this figure, this bifurcation structure. This is a bifurcating, we focus on the bifurcating branch. We can regard this bifurcation branch as a maximum value of the stationary solution. On the other hand, this means this solution branch is regarded as the minimum value of stationary solutions for each D, because this solution is a reflected solution is this one. So if we consider this parameter region A over alpha is in A and 1 moderate case, alpha is a moderate case, we can say this one, U is always greater than A, because this is a minimum value of the stationary solution. So U is always A. So this means when we consider the growth term, U greater than A means U. In order to make this pattern, U is used only this region. So this means that A is unstable and 1 is stable. So this is quite similar to the logistic growth case, because logistic growth case 1 is stable and 0 is unstable. So A is correspond to 0 in the logistic case. 1 is correspond to 1 in the logistic growth case. So we can expect that the behavior of solution is similar to that of the logistic growth in this case. Alpha is moderate case. So actually, we have, of course, stationary pattern observed, and corresponding to the simulation, we observe stable stationary spot observed. Moreover, in the case of logistic growth case, spatio-temporal chaos is observed. Actually, we observe the similar structure is observed. Some spatio-temporal chaos is observed like this. If we consider the 2D simulation, similar behavior is observed in this case. Spot is moving and two spots collide and form a single aggregate. And between aggregate, some new spot appear. This means quite similar to the spatio-temporal chaos in the chemotaxis-growth logistic growth case. So what is this case? 1 over alpha is less than A. In this case, solution global structure of stationary solution is like this. At this point, some solution profile, global structure solution branch appear like this. So when we focus on D, the relatively small d near here, then minimum value is less than a. This is a solution, constant solution of a. When we consider the small d, we observe the solution, minimum value of the stationary solution is less than a. So this means when we consider the growth term, this part 0 and a, this part is also used to make this pattern. When we focus on d, small d, to make this pattern, this part is also used. So we can expect the behavior of solution is different from that of the logistic growth case. So I show you some numerical simulations. This is a simulation for this case. Alpha is a relatively large case. So some aggregation pattern is observed, but eventually this pattern is disappear. As time evolved, U goes to extinct. So behavior of solution for this case, 1 over alpha is less than a, is completely different from the the logistic growth case. This is my conclusion. Thank you for your attention.